I'm teaching the basis for a topology. Lecture 19. Basis for a topology. Okay. First, I remark the basis in algebra. Basis in algebra. You know that R2 is two dimension. Okay. R is one dimension. And the other. Okay. Why R2 is two dimension? R2 is here. This is R2. R2. It has a basis such as I and J. Every vector in here, V, A, B, okay, I can write V, AI base of A plus BJ, okay, AI plus BJ. Then I can say that I and J, the set of I and J, is a basis for R2. Okay, I and J. Then R2 is two dimension. R2 is two dimension. Okay. Excuse me. Also R. This is R. Okay. I can choose this one. Okay. Every excuse me, I change my the color. Every every R belongs to R can be written as R times 1. For example, 3 is 3 times 1. Okay, I write it. Or, for example, minus 4 can be written minus 4 times 1. Then 1 is a basis for R. Then R is a one-dimensional space. R3. Okay. R3, you know that I, J, and K is the basis for R3. Okay. I, J, K is a basis for R3. Then R3 is three-dimensional. Okay. You know that by this method, I can say that Rn is n-dimensional space. Is a n is an n-dimensional space. Okay, this is algebraic definition of basis. Algebraic definition of a basis. Okay, we have a question. What is the topological definition of basis? Okay, here I define the definition of basis in topological space. In topological space. Okay, let uh, X and tau be a topological space. A basis for tau is a collection is a collection B of subset of X. I call these subsets as basis element called basis element. Such that it has two properties. One, for every X belong to X, there exists a beta of B of the basis such that X belong to beta. Beta is an element of this B basis. 2. If X belong to beta 1 intersection beta 2, beta 1 and beta 2 belong to B. Okay? Then there exists a beta 3 belong to beta A such that X belong to beta 3 and this is subset of beta 1 intersection beta 2. Okay. Then the set B is called a basis for topology. I give you the picture here. For example, this is a topological space, for example, X and 2. Okay? And this is basis, for example. Okay, you see that every element in X, for example here, okay, belong to a basis element is here. Basis element. Indeed, if you choose this is P, okay, P, this is P, you see that it is in an element of base. Okay. Also, if I choose an element P between intersection of these bases, for example, this is I choose another color. This is the basis. I call it B1, and this is another element of, I call it B2. Okay, and I choose a point in their intersection here. For example, P is here. Okay, I must find another element of their basis. For example, this one. Okay, beta 3. Okay, beta 3 contains P. P belongs to beta 3. Beta 3. Beta 3. And this is a subset of beta 1 intersection beta 2. Then I can say that beta I call it B, beta I belong to I, is a basis for topology. Is a basis for topology. Uh, in this case, uh, if B beta I belong to I, satisfies the two conditions, then we define the topology to generated by P. Okay, as follows. As follows. I give you the definition. A subset U in X. A subset of U in X. Okay, is said to be open. Is called open if for every element X in U there exists a beta belong to B such that X belong to beta, and this is a subset of U. Okay, then I say that topology tau is generated by P. Tau generated by P. I write it as follows. This is means generated by. For example, R2 generated by I and J. R3 generated by I, J, K. Okay. Then here I write that the top generated by P. Okay. For example, in your life, soup, soup, soup generated by onion, potato, water. I can say that hen and some other thing. Okay, soup. You eat soup and it is delicious. Uh, you use onion, potato, water, hen, and uh, some other thing, vegetable, vegetable. Huh? Okay, for making a soup, for making a soup. Here in topology, I say that a topology generated by P. Okay. When for every U in it, I call it open, and every element of U, there exists an element of this one, beta, such that X belongs to beta, beta is a subset of U. Okay. Okay. I give you two beautiful example here for you. Okay. Okay. For example, in R2, R, okay, uh, the circles, the circles, circles, daire. Uh, I write here B, B is the circles, all of circles in R2. Okay, B is a basis for R2. Okay, you see that every element in R2, for example P, I can have many circles that has this P. You see that? Yes. Okay. Okay. Then P satisfies the first condition. Okay. If you choose to a point here, for example P, and I choose two circles that has it, for example, this is another. I call beta 2 and this is beta 1. Okay. Then I can give you a very little circle here between them. This is, I call it beta 3. You see that P is belong to beta 3. Beta 3 is a circle and it is a subset of beta 1 intersection beta 2. Then the circles are a basis for R2. Okay, the circles is a basis for R2. In the topology generated by circles, a subset U is open if every x in U lies in some circular region contained in U. Okay, if you choose any point here, for example, x. Okay, you see that you have a circle beta 1 contains. If I choose here y, you have a circle contained. Okay. B is a basis for topology, and tau generated by this circle. Okay. Understand? Abdul Salam Taha. مولد قسان الحسناوي مولد. تشكر. Assalamu alaikum. Abdul Salam Taha. I don't see your friends in class. I don't know why they don't attention to the class. Okay. Okay. This is the definition of basis in topology. I can say that a topology have many bases. Okay. Okay. The circles is a basis for topology. There are another basis. For example, rectangle, mustatil. Okay. I choose R2. Hmm. If I choose a point here, P, you see that I have a rectangle here. Okay, this is beta 1. I can choose another. This is rectangle, beta 2. Another one. This is beta 3. Okay, rectangles are basis for R2, are basis for R2. If I choose a point here, for example, this is P, and this is a basis element. I call it beta 1. Okay? And this is another beta 2. You can see that I give you a little rectangle here, beta 3. You see that P belongs to beta 3. Beta 3 is a subset of beta 1 intersection with beta 2. Okay, this is the basis for topological space. Basis for topological space. Rectangles are bases. Uh, Also triangles. مثلث. مثلث. Triangle. Triangle. Okay. مثلث. This is R3, R2, R2. Okay, if I will choose a point here P, I can choose a beta 1. Okay, you see that P belongs to beta 1. If I choose here X, okay, and this is an element of beta 1, and this is another beta 2. Then I can choose a very little uh, very little مثلث. I choose here. Look at it. Okay. Beta 3. This is beta 3. You see that X belongs to beta 3. Beta 3 is a subset of beta 1 intersection beta 2. Uh, then the triangles is a basis for R2. Triangles is a basis for R2. Okay. in R3 space. R3 space. This is R3. R3. Okay. If you choose a point here, P, okay, I can give you a sphere, Cora, here, okay, I call it P, beta. You see that P belongs to beta, Core, a sphere, okay. The first condition of basis holds. If I choose a point here, for example, X, you can see that, excuse me, you can see that I have, for example, this is a sphere, I call it beta 1. This is another element that contains beta 2, okay. X, as you see, X belongs to beta 1 intersection beta 2, okay. I can choose an very little circle sphere here, beta 3. You see that X belongs to beta 3. Beta 3 is a subset of beta 1 intersection beta 2. Then spheres, a set of spheres, is a basis for tau. Indeed, I can say that tau is generated by a sphere. Okay. Okay. I come back to the definition of basis. Okay. Okay. Again, I repeat it for you. Let I choose the color. Okay. Let X tau be a topological state. A basis for tau is a collection B of subset of X. This subset is called basis element. Such that first, for every X there exists an element of B, call it beta, such that X belongs to beta. This is the first condition. And the second condition says that X is belong to intersection of two elements of B. There exists an element of be beta 3. Here is beta 3. Such that x belong to beta 3 intersection of is a subset of beta 1 intersection beta 2. Okay. I give here some examples. Okay, this is the first examples in R2. Okay, you see that every element here, X, I can choose a circle. Okay, if Y is here, I can choose another. If here, I can choose another. Okay, every element I can choose and circle contains it. Okay, and if here, this picture, uh, if P is a point here that beta 1 and beta 2 contains E, indeed pair belong to beta 1 intersection beta 2, I can choose a circle here. You see that? You see that? Beta 3. You see that P belongs to beta 3. Beta 3 is a subset of beta 1 intersection beta 2. Then the circles of R2 is a basis for R topology. Okay? The set of circles is a basis for tau, and I can write tau generated by circles. Okay? Another basis is rectangle, mustati. Every element is here P. You see that I can choose a rectangle beta. Okay, P belongs to beta. I can choose here X. I give you another rectangle beta. Okay, X belongs to beta. Beta is rectangle. If I choose here this picture, attention. Okay, this is beta 1 here. I call it beta 1, and this is beta 2. Beta 2 is here, and they contain P. P is here. P is here. Then you see that I can give you a little rectangle, green rectangle. You see that P belongs to beta 3. Beta 3 is a subset of beta 1 intersection beta 2. Then rectangles is a basis in R2. Okay, in R2. And also uh, I give another basis. This is triangles. Musallas. Okay. Uh, ellipse. I can choose ellipse here. Ellipse. Ellipse. Basic. We say basic in Persian. In R2, The first condition holds. The first condition holds. The second condition says that if I have P here and there exists two element of, okay, this three. You see that P belongs to beta 3. Beta 3 is a subset of beta 1 intersection beta 2. Then ellipse, the set of ellipse is a basis. Okay. Understand, everyone? Understand? Okay. تشکر محمد الخفاجی. I finish my teaching here. I come back to you after 10 minutes. I finish here. My teaching here. I come back after 10 minutes. Okay? Okay. And I am teaching standard topology on R. Standard topology on R. If B is the collection of open intervals in R, indeed of B, that is defined X such that X between R and B. The topology generated by B is called standard topology. On R. Okay? Indeed, the basis for R, this is R. Okay? The basis topology for R is intervals. Okay? Intervals in open intervals give a topology on R, I call it standard topology. A standard topology. Okay. Indeed, B, the basis is open interval. B belong to R. Okay. This is the basis for standard topology. B is a basis for standard topology on R. Okay, I can choose another basis. Here. Before I give another basis, I check that there is a basis or no. Okay. If you choose any point here, for example P, okay, you see that you can choose an interval here, P minus 1, P plus 1. Okay, you see that P belong to P minus 1 and P plus 1. The first condition holds. Okay? If you choose X here, for example, and choose two intervals here, for example, this is A, B, and another, for example, this is, for example, C, D. Okay? I can give you another basis here. Attention. I can choose D and A. D and A. You see that A, D. Okay? This is an interval. I can write here X belong to A and D. This is a subset of AB intersection with C. AB intersection with C. Okay. Then the second condition holds. Then there is a basis for a standard topology on R. I give you another basis. B prime is here. A and B. From the left close and from the right is open. Okay. A and B is the X that X little than B and greater or equal to A. The prime is another basis. And the topology generated by B prime is called lower limit topology. Lower limit topology. Lower limit topology on R. On R. On. Okay. I check for you. This is a basis. If you choose any point here, for example P, okay, I give you P minus 1, P plus 1. You see that P belong to P minus 1 and P plus 1. Okay. The first condition holds. If you choose another point here, for example, I call it X, and choose two basis elements, For example, this is A and B, and another, for example, C and D. Okay. Uh, I can give you this one, C and D, C and D. Okay, C and D. You see that X belong to C and D, and this is an intersection A B intersection with C. Then the primitive basis. The primitive basis for topology of limit lower topology. Limit lower topology. Okay? Okay. Mhm. Okay. Then we have uh, uh, upper limit topology. Upper limit topology Bezegon defined by A and B from the right clause, and this give you upper limit topology. Upper limit topology on R. Okay. Then we have three topology on R. Three topology on R. For R, we have three topology with B defined by A, B, open interval, B prime, and B second. It's called, the first one called standard topology. This is lower limit topology. And this is upper limit topology. Okay. Uh, okay. Everybody understand? Understand? Upham? تشکر Ali Al-Shahmani Muhammad Al-Khafazi. I enable the microphone for you. If you have any question, I give you answer. If you don't like to talk with microphone, or you have not access to microphone, you can write in the below in icon, and I read your sentence and answer to your question. Okay. Uh, okay. Okay. Subbases. تشكر عبد السلام طه. تشكر. شكرا جزيلا. Okay. What is subbasis? What is it? Okay. I define it for you. A subbasis is for a topology on X is a collection of subset of X whose union equals X. Ali Al-Shahmani, please let me, I finish my teaching. After that, I answer to your question. Okay. Indeed, a subbasis for a topology on X is a collection of subsets that union is equal to X. The topology here. The topology generated by S is defined to be a collection of all unions of finite intersections of elements of this. I explain it for you. Indeed, for example, this is topological space. Uh, a subbasis is, for example, is a subset of X that such that their union, I call it Si, S alpha belongs to I. Their union is X. Their union is X. Okay. This S alpha, give you a topology. Okay. Uh, I call it tau. What is tau? Tau is union of finite intersection of Si. I from, for example, 1. Okay. Uh, 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 I delete for you the subspace. Subspace is almost hard for you to understand. I only define for you. Define for you. Okay. However, we have order topology. Order topology. What is it? Okay. Order topology. Uh, let X with this element be a ordered set. Order, what is mean? This means that for every A and B, I can say that A in X. I can say that A little than B or B little than A. They can be one of them wholes. Okay. Okay. For example, A less than B. Okay. Okay. There are 4 intervals. Defined by A and B. The first one is B. What is it? X such that X between and B. A and B close. The subset of X that are greater than A but less or equal to B. A and B. The elements that greater than A or equal and less than B. And we have closed interval X defined by, okay. This is open, and these are half open, and this is closed, closed interval, closed interval. Okay. Uh, Now I define the order. I define the order. Let uh, X be a set with order relation. X and, for example, this be a ordered set. Okay. Let B be the collection of all sets of the following type. One, all open interval, all open interval A, B in X 2 all interval A0 and B. A0 is the smallest element of X. A0 is smallest in X. 3 all intervals are A and B0. B0 is the largest element in X. Okay? The collection B is a basis for a topology on X, which is called order topology, which is called order topology. Topology on okay. I must say that if X has no smallest element, okay, smallest element in the case 2, smallest. If there is not smallest or largest, uh, then we have not the type 2 and the type 3. Okay, only we have the first one. Only we have the first one topology. Okay, for example, I give you example in R. In R, standard topology. We have standard topology. Okay, is a order topology. Is a order topology. Okay, is a order topology. A and B. Okay, you see that A is less than B. Okay, A is less than B. Okay, we have uh, another example. The positive integer z. What is it? 0, 1, 2. Okay, is ordered set with smallest element. Is a is an ordered set with a smallest element. Okay, here we have 0 as the smallest element. You see that then I can define the order topology on Z. Okay, I can define the order topology on Z. How I can? Here, attention. The ordered set, ordered topology. Excuse me. ordered topology on Z plus is a discrete topology. Is the discrete topology. For every 1 point set, 1 point set is open. If n is greater than 1, then the 1 point set n, for example n, can be written as n minus 1, n plus 1. Excuse me, I choose open. Open. Okay? Okay? Is a basis element. Okay? In this 1, 2, 3, 4, 5, 6, and every of elements is a basis. Is a basis. Okay. 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 I think that you are tired and I finish my teaching here. I give you this PDF file. Okay. I teach from basis to product topology. Product topology. In the book, we are in page 86. I teach before than product topology. I hope you understand all notions that I teach. If you have any question, I'm in your service. I help you. If you have not any question, you can leave the class. تشکر. شكرا جزيلا and goodbye everyone.